sac225 problem number 1. Looks like a law of reflection problem. They want to know, given some light shining, as indicated, where on this wall is the light going to hit? Let's continue this line to indicate diagrammatically where it'll hit, and then see if we can solve for it. We'll have normal to the mirror. This I would call the angle of incidence. Theta I, and this is the angle of reflection. Theta R, and by the law of reflection, theta R is equal to theta I. So to find this distance, that's what we're looking for. We'll call it y prime. Call that x prime. X, let's call this y. I need this angle, which is going to be, I'll call that theta prime. But it's going to be 90 degrees minus theta r, which is, this is the same value, and this is 90 degrees minus theta I. So this, being theta, is going to be equivalent to theta prime. Theta prime, therefore, is equal to theta. So we get theta, we get theta prime. Well, we're going to need to know what x prime is, or what, in order to get y prime. Let's work on this triangle. Looks like we'll be able to get theta from this triangle. Indeed, we can also get x from this triangle. So if we get x, then x prime is going to be 2.4 meters minus x. We'll have that. And if we get theta, we know theta prime is equal to theta, and we'll have a side and an angle for this triangle. I'll go ahead and shade it so you know what I'm talking about. For this triangle, the prime triangle, and with a side and an angle, we'll be able to get the desired quantity. So let's proceed with that. I'll say x to start with over the known value of y is, with respect to this angle, which I think I'll call phi, is the opposite over the adjacent, so that's the tangent of phi, and therefore x is equal to y tangent of phi. Which is equal to 1.80 meters times the tangent of 38.0 degrees, and that yields 1.406 meters. Keep in 4 places for an intermediate result. Eventually we got to round things down to 3. Okay, now let's get theta. I think the easy way to look at theta is the angles, aside from the 90 degree angle, the 2 angles in a right triangle have to add up to 90 degrees. So theta plus phi is equal to 90 degrees, or theta is equal to 90 degrees minus phi, which is 90 degrees, and we're going to consider that an exact value, minus the 38.0 degrees, or theta is equal to 52.0 degrees. And that makes theta prime equal to 52 degrees, because that's equal to theta. And that came about because of our law of reflection. Theta r is equal to theta I. And x prime plus x is equal to this 2.4 meters, which I'll call d. So x prime is equal to d minus x, subtracting the x from both sides, which is the 2.40 meters, minus the 1.406 meters, which is 0.994 meters. That's really good to 2 sig figs, and I'm carrying an extra one. One significant digit, or 2 digits past the decimal, so it's only good to that place, making it a 2 sig fig value. And then, looking up at the triangle here, at which we seek the y prime divided by that x prime, with respect to theta prime, that's opposite over adjacent. So let's go ahead and write that down. Y prime over x prime is equal to opposite with respect to theta prime. Opposite over adjacent is the tangent. So I got tangent of theta prime. Now I can solve for y prime. That's x prime times the tangent of theta prime, which is 0.994 meters times the tangent of 52.0 degrees. Y prime is equal to 1.272 meters. Okay, this is really only good to 2 sig figs. So around the whole result off to 2 sig figs, I get 1.3. meters for my final answer. Let's make sure that I answer the question, where on the wall does the beam hit the wall? Specify your answer as a horizontal distance measured from corner A. So y2 is indeed that horizontal distance, 1.3 meters from A. And that's the solution for SAC 225, problem number 1.